Here in Nevada, on the western edge of America's Great Basin, the Earth's natural heat is converted to electricity by a new geothermal power plant technology. The plant's capacity is 9 megawatts, small by normal industry standards, but large in terms of the technical advance the plant represents. A technical advance to accelerate the development of a vast, relatively untapped natural resource. A resource that could produce 25% of the West's electricity in 30 years. The key to this high-performance advantage is the Rotary Separator turbine. To understand how the Rotary Separator turbine helps to maximize the use of a geothermal resource is to first explore the nature of geothermal energy itself. The heat that drives this power plant is extracted from a natural hot water reservoir 5,000 feet below the plant. The energy that heats this hot water comes from deep within the Earth itself, a searing 5,000 degrees at its center, and around 1,800 degrees Fahrenheit at the base of the crust. The crust, thin as an eggshell in proportion to the Earth's diameter, is quite thick in terms of our ability to penetrate it, to reach and use this source of heat. But using this heat comes into the realm of the possible in areas of geological activity where the crust is fractured and thin. The West's Great Basin. In this vast land, bounded on the east by the Rocky Mountains and the west by the Sierra Nevada, there are many areas where the crust is fractured and relatively thin. It is in these areas where nature works for man, storing the heat in a usable form that can be reached from the surface. Heat from the Earth's hot interior transfers by conduction to porous and fractured rock deep within the crust. Water seeps into the pore space in the hot rock. Heated, the water tends to circulate vertically in the reservoir. It is the heat of this geothermal resource, the hydrothermal reservoir, that is converted to electricity. Hydrothermal or liquid-dominated reservoirs are divided into two classes, moderate and high temperature. High temperature means that the liquid or geofluid is hot enough in its natural state that when flashed, it produces a significant quantity of steam. It is the geofluid from the high temperature resource the Rotary Separator turbine efficiently converts to electricity as a component of a flash steam power cycle. The flash power cycle begins when the geofluid is drawn from the reservoir through wells. Hydrostatic pressure keeps the geofluid in its natural state from boiling. When a well valve is opened, pressure forces the geofluid up the well. As the fluid rises, its pressure drops, and it begins to flash to steam. In a single-stage flash system, a simple separator is used to separate the steam from the remaining geofluid. In a two-stage flash system, a second separator or low-pressure flash tank is added to cause more of the geofluid to flash to steam. When the geofluid leaves the well, it has a high velocity. Most of the kinetic energy is imparted to the geofluid's liquid fraction. The kinetic energy is lost in a conventional separator.
This is the view that shows how the Rotary Separator turbine efficiency advantage can be obtained with standardized equipment for any resource from 350 up to over 500 degrees.
Looking for ways to increase the performance of flashed steam plants and to reduce the cost of power generation from liquid-dominated reservoirs, a research program was undertaken to prove the feasibility of the rotary separator turbine.
On the rim of the rotary separator.
The rotary separator turbine was developed to use the kinetic energy of the geofluid. It replaces either the separator, the flash tank, or both in the flash steam power cycle. The working components of the RST are 4 injection nozzles, a rotary separator, a hydraulic turbine, a transfer rotor, and a stationary scoop. The geofluid from the well enters the nozzles of the RST. As fluid flashes in the nozzle, it expands and accelerates. The result is a high-velocity jet of liquid droplets and steam. The force of the jet spins the separator. Centrifugal force holds the liquid in the rim of the separator. The kinetic energy of the high-velocity liquid spins the RST's hydraulic turbine, producing usable shaft power. The liquid leaves the hydraulic turbine to the rim of the transfer rotor. The stationary scoop picks up the liquid and repressurizes it for reinjection at the edge of the reservoir. When the RST is used in a single-stage system, a 20% increase in electrical yield is realized. When the RST is used in the second stage of a 2-stage system, a 7% increase in output per pound of geofluid is realized. In 1981, a 1,600 kilowatt unit was installed on the Roosevelt Hot Springs Reservoir near Milford in southwest Utah. The project was a joint effort of EPRI, Utah Power and Light, Biphase Energy Systems, and Phillips Petroleum. The RST was run through its paces for 4,000 hours to map performance and to demonstrate operational readiness. The test confirmed a predicted performance advantage of 20% over that of a single flash plant. During the 4,000 hours of testing, the prototype unit demonstrated an availability factor of 98%, showing readiness for commercial application. The turbine is designed to adapt to a range of reservoir conditions. Interchangeable turbine buckets, turbine nozzles, and liquid discharge diffuser adapt the same basic frame size to match a broad range of reservoir temperatures and pressures. At Desert Peak, Nevada, the first commercial version of the RST uses the same basic design that was tested at Roosevelt Hot Springs. The rotary separator turbine provides greater flexibility and higher performance at a lower cost, helping utilities unlock the vast, relatively untapped, high-temperature geothermal resource. Desert Peak joins the Geysers, East Mesa, Salton Sea, Heber, Milford, Casa Diablo, and Biawawi family of geothermal power plants, leading the way to our energy future.